Unit 6, Section 4. Today we're taking a look at exponential growth and decay, which are some of my favorite topics in mathematics because they pertain to how we can grow our money and become wealthier individuals. An exponential growth function, remember, takes on this form of y equals a times b to the x. We said a was our initial amount and b was our growth factor. Well, growth is going to occur when b is greater than 1. Anytime we multiply a number by something larger than 1, it's going to increase. So you can kind of think of your growth factor like this, 1 plus r, where r is the rate of growth in decimal format. For example, if we had a 4% increase, then our b value, our growth factor, would be 1 plus 0.04. 0.04 is the conversion of 4% to a decimal. That would make my b value 1.04. So you can see that that's slightly larger than 1, and therefore whatever initial amount you have will be growing. Likewise, if we had a 15% appreciation, which is just a fancy way of saying growing in value, then that would be 1 plus 0.15. 0.15 is the decimal conversion of 15%, and that would convert to 1.15 as a growth factor. Again, that's larger than 1, and therefore whatever our initial amount is will be growing. Let's do an example. The inaugural attendance of an annual art festival is 80,000. The attendance increases 6%. So keywords here, increase 6% each year. Write an exponential growth function that represents the attendance after t years. All right, so remember we're going to say our initial amount, its beginning amount was 80,000. The growth factor will be 1 plus our percentage rate of 0.06. That's just converting 6% to its decimal format, raised to the t number of years. All right, so if we want to evaluate this now for the 5th year or make a prediction how many people will be in attendance in that 5th year, then we're going to multiply 80,000 times 1.06 to the 5th power. We're going to let our calculators do that for us, and our calculators will follow the correct order of operations, which will be to do the exponents first, then multiply by 80,000. That's going to result in 107,058 attendees. All right, so that's exponential growth. Let's talk about exponential decay. Exponential decay is going to occur when a quantity decreases by the same factor over equal intervals. Now you can kind of think about your exponential function here as a, our initial amount, times 1 minus our rate of decay in decimal format. All right, so for example, let's say we had a 5% decline in attendance. That would be the decimal 1 minus 0.05, and therefore our growth factor would be 0.95. Now our growth factor here is going to be less than 1, because anytime you multiply something by a number less than 1, it's going to be decreasing or shrinking. Likewise, let's say we had a 17% depreciation, which is pretty common for certain types of cars. Year over year, their value decreases or depreciates. That would be 1 minus 0.17, and that would translate to a growth ratio of 0.83. Again, that's less than 1, and therefore the value would be decreasing. So in example 2, we want to determine whether each table represents exponential growth or exponential decay. And our little hint here is to look at our y values. What's happening to our dependent value? Dependent value, as our independent value is changing. So here our y values look like they go from 24 to 12 to 6 to 1/3. Our constant percent rate of change is 50%. They're going down by 1/2 each time. We're multiplying by 1/2. So when we multiply by a number less than 1, this would be depreciation or declining or exponential decay. In our next example, we see that 4 goes to 40, 40 goes to 400, 400 goes to 4,000. We are increasing by multiples of 10. So that constant percent rate of change now is 10. So this would be exponential growth, and that's the kind of growth you want to see your money take on year over year, 10%, or sorry, 10 times growth. All right, let's get into some word problems here. Suppose a new piano costs $8,500 and depreciates. Remember, that's a fancy way of saying declines or loses value each year. Write an equation that gives a piano's value when it is t years old. So we're going to say y is its price after t years. It starts off at $8,500 and its growth ratio is 1 minus 0.06%. Well, 0.06 I should say. That's the decimal form of 6%. And then we're going to raise that to the t number of years. All right, if we clean that up just a little bit, we got 8,500 times 0.94 to the t. Again, my growth ratio here, or my growth factor, is less than 1, so this initial value is going to be decreasing t years down the road. All right, let's predict, or let's actually calculate the value of the piano 5 years from now. That would be 8,500 times 0.94 to the 5th power. Again, letting our calculator do that work, we should come up with $6,238 and a little bit of change. All right, let's flip the page over here. In example 4, it just says determine whether each function represents exponential growth or exponential decay. Now they're giving us equations rather than tables of values. And our hint here is to look at our growth factor. Our growth factor is the one that is the base that has the exponent on it. So if our growth factor b is greater than 1, remember this is going to signify growth. And this is going to specifically be 9% growth over x time periods. In our second example here, you can see that our growth factor here is less than 1, so that's going to be decay or decline. More specifically, this is going to be losing 7% each x time periods. All right. Now we get to my favorite part here. We're talking about money, and we're talking about compound interest. Your parents will often tell you that money doesn't grow on trees. However, you can grow money. So, compound interest, Albert Einstein said, is the 8th wonder of the world. Highly encourage you guys to look into it or take consumer finance your senior year. All right, so let's talk about this formula. This is just the format of y equals a times b to the x, but we have some fancy things in here for a and b. A represents our initial amount, and that's P, the principal. This is what you deposit into a savings vehicle. 1 plus, that's very similar to our growth up above, our growth factor up above. And then we have R divided by N. Well, R is the interest rate at which your money is growing, and N is the number of times it gets compounded within a year. And T represents the number of years you leave that money in that savings vehicle. All right, so let's just go through some common compounding time frames here. Something might be compounded annually, and that would be an N value of 1. If something's compounded semi-annually, our N value here would be 2. Compounded quarterly, well, that's every 3 months, and that's 4 times a year. Monthly, there are 12 months in a year, so that's 12 times. Daily would be 365. And then finally, if we're compounding something hourly, there's 8,760 hours within a year. So let's try an example here. In example 5, it says that you deposit $300 in an investment account that earns 3% interest. Annual interest, that's the key word here. Compounded monthly, that's the key word, not annual. We'll go with compounded monthly. All right, so that means my N value here is 12. I deposited 300, that's my P value. My rate R, got to convert that to a decimal, is 0.03. And it says you also have a savings account that has a constant balance of $100. All right, so let's first of all answer question A. It says write a function M that represents the balance in dollars of the investment account. Don't worry about the savings account. after T years. All right, so M is equal to my $300 deposit times 1 plus my interest rate, 0.03 divided by 12, all raised to the 12 times T number of years. All right, next it says in part B, write a function B that represents the total balance of the two accounts after T years. Then find and interpret B of 5. All right, so we have our B of X account is going to be exactly what we have up above, 300 times 1 plus 0.03 over 12 raised to the T power. But remember T, or I should say X power, well, our T is going to be 5. All right, so we're going to evaluate this for 5. Plus, now remember your savings account has a constant balance of $100. Now we're just going to add 100 there at the end. All right, so we're going to let our calculator do the work here and see what we come up with. We're going to, all right, we have our $300 times our 1 plus, now we're going to open up parentheses and do 0.03, divide that by 12, close that parentheses, close another parentheses, and then do our exponent of 12 times 5, and that's going to be what we have in our bank account there, or sorry, an investment account. But remember, we need to add $100 to that because that's going to be the combination of both of those accounts. So $448.49. All right, now that's a good little lesson in compound interest. You can grow your money and accelerate your wealth. All right, more about that tomorrow in class.